Greetings, fellow particle people, dynamics dabblers and node noodlers. In this tutorial, I will dive into the realm of the new and shiny particle constraints. So what are particle constraints and what are they good for? The particle constraints extract the position or rotation of an individual particle and, well, let you do with it what you will. Perhaps the most common use case would be to have an item follow a particle. Note that this means any item, not just geometry. So, for example, we could constrain locators, particle emitters, deformers, forces, basically anything with a position or transformation. Indeed, other particles can also be constrained in this way, but in my excitement I'm getting ahead of myself. Here is a system, a particle system, wound up and ready to play. But this system needs attention. It's particle constraints today. So what we would like to do is make this cube follow one of the particles. Okay, so just like with other constraints, what we need to do is select the object that we want to constrain and the object that we want to constrain it to. So in this case we want to constrain the cube. For convenience, let's bring the cube into the schematic. Select the cube and the particle simulation, and now the particle position constraint becomes available, as does, with a right click, the particle rotation constraint. So let's go for particle position first and have a look and see what's been built for us. We have the particle constraint connected to the particle simulation, that's the source of our particles, and that's been wired into the world position of the cube. So what happens if we run the simulation? Okay, well that's a little unexpected. The problem is that we haven't told the particle constraint which particle it should be following. Let's have a look at the properties of the particle constraint. The particle ID is 0 and we have closest ID checked. That means that this particle constraint will try and find the closest ID to 0 and it will follow that. But the closest ID to 0 changes all the time. A bit of explanation is probably in order. The particle IDs are generated as the particles are created, and the IDs lie between 0 and 1. But I don't think particle ID of 0 is ever generated. So if we have a particle ID of 0 as our selected particle ID, it's going to be jumping to whichever particle ID happens to be nearest to that 0. So for example, if we unchecked the closest ID and ran the system, we would not expect the cube to follow any particles. What we need to do is select a particle ID that we know is going to be generated. Well, I happen to know that 0.25 is a good one. Let's try that. Excellent. We're now following one particular particle in the simulation. Once that particle has died, the cube is then abandoned back at the origin. Right, well it's not really much fun trying to guess the particle IDs. The way that they're generated is somewhat mysterious, so it goes 0.5 and then 0.25 and then 0.75 or something like that, and it keeps bisecting in the floating point range from 0 to 1. But we have a handy little tool to help us. If we add in from the other menu the particle ID generator and wire that in to the particle ID of the particle constraint, we can then select which particle we want. So index 0 we would expect to be the first particle. Maybe we don't want the first one, maybe we want the 12th particle. And if we run the simulation, the cube should sit there for a bit, and then when the 12th particle is emitted, it'll grab hold of that and follow it. There we go. Superb. Okay, so now we would like to follow the rotations of the particles. So it's the same procedure. We select the cube and the particle simulation and then select particle rotation. And if we double click, we'll see what's been created. We have the particle constraint rotation now connecting our simulation to our cube's world rotation. Let's just swap these over just because I don't like tangled up connections. Okay, so this constraint doesn't know which particle it's talking to. It's probably a good idea to use the same ID for both of these constraints, but you don't have to if you don't want to. Let's add the channel Particle ID and wire it up. And now let's run the simulation again. Okay, well, but the cube isn't spinning. Why not? Well, that's because the particles are not rotating and we need to make them rotate. Well, I could do it by hand, or I could use one of the built-in assemblies that are there for these sorts of things. I don't think I've shown these in any of my previous tutorials, so let's have a look at our assemblies. And you'll find a folder called Particles within the Assemblies folder, and in here are a bunch of useful particle effects. And somewhere in here we will find spin particle, and that's just what we want. We want to give the particle some spin, so drag the assembly in and connect up this connection here, which is internally connected to a particle operator. Connect it to the particle simulation, and we need to set the rotations per second in the X, Y and Z axis. So let's go for, I don't know, 180 degrees per second in X, nothing in Y, and 150 in Z. Now the particle should have some spin on it, and the constraint should show that up for us. Well, would you believe it? It's actually working. In this example, let's do something a little bit more unusual. So let me just review what I've created in this scene here. The geometry is fairly straightforward. I have an inside-out ball and an outside-in ball, I suppose you'd call that one. We have a solver and a particle simulation, as you'd expect, and the dynamic collider has been placed into the system in order to bridge the particle simulation to the solver. So if I just run this simulation as is, we should see some particles emitted and they bounce off the inside-out ball. So they're constrained within the sphere. Why I've only got two particles? Because I have a single vertex in the center of the sphere connected to this source emitter, and the source emitter is set to pulse mode, and I just have a couple of pulses right at the start. So what I'm going to do is connect a magnet deformer to the particle. The idea being that the magnet will bounce around inside the sphere, and as it gets towards the edges, it'll deform the surface. So if I'm going to have a magnet deformer, let's put one into the scene. And I'm going to do all of this by hand rather than by using the automatic buttons, so that you can see how the schematic is built up internally. So let's create an effector, and we want a magnet effector. Add that to the schematic. We'll need an influence, so let's create a general influence. Add that to the schematic, and this is what would be created for you automatically if you just clicked on the magnet button over here. So let's connect the magnet effector into the effector for the general influence, and we want the magnet to affect the outside ball, so let's connect the outside ball to the geometry of the general influence. Okay, so the magnet is active now and it's done something really unpleasant to our sphere. So let's change some of the settings for the magnet effector. Let's reduce its range to, let's say, about 120 millimeters. And let's increase the solid core to about 100 millimeters. And when this bounces around, it should then affect this outer surface and create a, well, hopefully an interesting effect. So we want to connect the magnet effector to the particles in this particle simulation, or at least to one of the particles in this particle simulation. And to do that, we use good old particle constraint. So let's add into our system a constraint, particle constraint, position, and now we can wire this up. So the particle source is the particle simulation, and the thing we want to affect is this magnet effector. We haven't got any way of affecting it yet because we haven't got the channel exposed, so let's just select that and pull in the world position of the magnet effector. And now we can connect the output of the particle constraint into the magnet effector. And there's one last thing we need to do. We need to tell it which particle we're interested in. So let's add the Particle ID channel, and where is it? Here we are, down here, Other. We'll have our Generate ID, and the ID goes into the Particle ID. Let's connect that up to Particle 1. Now when we simulate, we should hope that the magnet effector will follow the first particle. And it does. And look at that. It's actually deforming the surface. But I don't really want it to deform it in that way, so I'm going to change it to a repulsive force so that it pushes the surface out as it approaches it. I think that would look more interesting if we sped up the particles. So let's increase their initial velocity. Let's double it. Of course, we can do exactly the same thing for the second particle and add a second constraint. So I'll do that very quickly. You'll be amazed at the speed of my mouse clicking. There, I think I've got everything into position. We should now have two magnet effectors dancing around inside of our ball. But we don't, because I haven't connected up the particle simulation. Let's try again. There. Super. So they're both bouncing around inside the sphere, pushing it around, creating those interesting bumps. In this next example, I'm going to follow not one, but 4 particles. Whoa, steady on there. So as you can see, the sphere is interpolating between particles and then looping back to the beginning. So at any point in time, the sphere is always interpolating between 2 distinct particles, and those will be particles n and n plus 1 until we get to 4, and then we loop back to 1 again. Okay, enough of that. So how do we arrange for this? Well, here is the sphere, and the position is controlled by this assembly, which I've called vector LEPR. So the vector LEPR will interpolate between position 1, that's the position of the first particle, and position 2, naturally the position of the second particle, according to the value of this alpha interpolant. So this alpha value will vary between 0 and 1, and you'll either get all A, all B, or somewhere in between, depending on the value of alpha. So where does alpha come from? Alpha comes from this relationship here. And if we look at the graph, you can see that we've got this curve that controls the precise behavior. So let's edit this just to see what the effect would be. Let's make it more sharp and run the simulation again. See that the motion of the sphere is now more linear, whereas before it had a gentle ease in and ease out. But where do the positions of the particles come from? Well, as you might imagine, these nodes here are particle position constraints, and the particles come from this particle simulation, and the rest of this system is very straightforward. We have a plane which naturally has 4 corners, and those are the things that are going to be emitting using this source emitter, which has some pulsed emission right at the start to generate 1 particle per corner. Right, the slightly tricky bit here is to make sure that at any point in time we're interpolating between particle n and particle n plus 1. So to generate our particle IDs, we use this generate ID node, which is taking an index and converting it into one of these particle IDs, the things we don't really need to know what they are. So for the index, we want to generate 1, 2, 3, 4, 1, 2, 3, 4 as time passes. And to do that, I take the frame number, divide it by a number of frames that I want the interpolation to take place over. So this number here can be, for example, 12 frames, in which case the interpolation will happen over a space of 12 frames. And then I modulo the result of that division by the number of particles. And then there's just a little bit of fiddling around to add 1 to it to make sure that the index goes from 1 to 4 rather than from 0 to 3. I think possibly it's easier to understand what's going on by looking at the values of these channels. So let's cache the simulation. And let's scrub through the timeline. So what should we look at first? Let's look at this divide node. So at the beginning of time, the input from the time node is 0. The number of frames is a constant, that's 12, and the result is 0. So as I scrub this along, the result is going to be essentially the number of frames divided by 12. We can check that at 120 we should get 10. Oh, we do. Excellent. So now we want to turn that into values that can be used for our index. So this modulo function will do it modulo the number of particles, that's 4. So let's look at the output of the modulus. Starts at 0, and the input on A is the result of the division. As you can see, it's gradually going up until we reach the value of 4, and then it wraps back round again. So the critical thing is that we get a number coming out here which has a value from 0 up until it's nearly 4, and then it wraps back round to 0 again. And then if we add 1, look at the result of the addition. We should start at the result of the add 1 is going to be 1 all the way up to 4, and then before we reach 5 it wraps round back to 1 again. So the upshot of all that blather is that this generator is going to be receiving an index from 1 to 4, and then it's going to be converting that into an ID. So the particle ID here is going to be for particle 1, 2, 3 and 4, and then 1, 2, 3, 4, 1, 2, 3, 4 and so on. What we would like is for the second particle to have the same particle IDs as this one but offset, and the amount we want to offset them by is the number of frames that we're interpolating between the particles. And we can use this rather nifty node called time offset to do that. If we feed in the offset time that corresponds to the number of frames that we're using for our animation and divide it by the frames per second, we'll get the appropriate offset. So let's have a look and see what the results are. So let's have a look at the result of the generate ID node. So at time 0 we have ID 0.5. At time 12 we have ID 0.25. At time 24 we have ID 0.75, then 0.125, and then we loop back to 0.5. So these are the particle IDs that correspond to the indexes that we're inputting into the generate ID node. So remember this sequence: 0.5, 0.25, 0.75, 0.125. And what are the results from the offset node? Starting at time 0, 0.25, 0.75, 0.125, 0.5. Phew! Right, okay, so there's just a little bit more fiddling around here, and this little bit of jiggery-pokery here I'm just using to take the fractional part of this calculation and using that to drive this relationship so that we can move along that curve and generate the interpolation between the particles. And I think that's just about it. So the interesting thing is that without changing anything in the rig, we can adjust the number of frames to give a different interpolation speed. So if we change that to 6, for example, it should go twice as fast. And if we change it to 30, it'll go really slowly. Okay, I think that's all there is to say about that rig. Let's move on to something else. In this final example, I'm going to make particles follow other particles. So in this rig I've got two particle systems, the lead simulation and the follow simulation. If I turn off the follow simulation, I can just play the lead simulation and then you can see what that's all about. So it's just a simple system with a couple of forces and a radial emitter producing this little whirlwind. And what we're going to do is we're going to extract the positions of these particles and use those to adjust the velocity of the particles from the following simulation. So let's stop that and I'll show you how that's done. Let's re-enable the, so try and click on the right thing, re-enable the follow simulation. Well, let's just have a look and see what I mean. So the particles from the follow simulation are attracted to the particles in the lead simulation. And so they stream eagerly from this emitter and chase the particles in the lead simulation. Right, so how is that done? Well, since this video is all about particle constraints, we use a particle constraint. So we have a particle operator attached to the following simulation, and we extract from those particles the position and the particle ID. The ID of the particle is fed into this particle constraint. So for each particle in the following simulation, we extract its ID, and we use that to extract the position of the corresponding particle in the lead simulation. So that position is given to us as a matrix 4. We need to extract that and turn it into a vector. That's just an x, y, z position for the particle. We can use that using the matrix vector node. We'll take the output of that, that's the position of our particle in world space, the position of the lead particle, and we'll feed that into this vector subtract node. So we'll take the difference between the position of the lead particle and the particle in the following simulation. That will give us a heading between the followed and the following particle, and we can use that as a velocity. So I'll bung that into a vector scalar multiply node just to scale the size of the velocity, and for some reason or other I've chosen a scale factor of 3, and that then feeds into the same particle operator to set the velocity of the following particle. There. Probably takes a little bit of looking at to get the hang of what's going on, but it does the trick. And just to add a little variety, I've actually animated the velocity amount. You can look at it in the graph editor. There we go. So I scale it by 0 for a period of time, and then by 5 for a period of time, and then by 0, and so on. Just repeat that graph. So the particles will alternately have 0 velocity and then a velocity that's taking them towards their sibling particles in the other simulation. Let's run that and see what that does. Oh, whoa, attraction, and then stay still, attract, and then stay still. So that's it for another exciting episode. I'm sure you can think of much more creative and exciting things to do with the particle constraints than I've shown, but hopefully that gives you the basis with which to make your own creations. I hope this was helpful, and see you in the next tutorial.